Welcome to today's webinar with Summation Research. Thank you for joining us. Feel free to ask questions during this webinar and our team will get to your questions right away. This pilot episode is kicking off a webinar series, The Future of Mission Readiness. Episode 1 is about data quality metric, or DQM, and how it is related to telemetry and flight testing. But first, a little bit about our company, Summation Research, SRI. Summation Research Incorporated, SRI, is based in Space Coast, Florida, just south of Cape Canaveral. We design and manufacture telemetry instrumentation for civil and Department of Defense flight test ranges, satellite ground station equipment, instrumentation health and status management tools, and data radios for transportation markets. Let's go to the next. These are the key objectives that we're going to be covering in Episode 1, Data Quality Metric. We will dive into the details of the why data quality metric was started, list different test methods for capable hardware, and we'll even show you DQM live. Get your notepads ready. There are several topics we need to cover. Topics to be covered in today's webinar. What is DQM? Why DQM? The history. What is DQE? How to assess the data quality. Benefits integrating DQM. Data quality calibration. DQM test methods. SRI's live demonstration. And then a Q&A. Let's go ahead and get started. DQM history and the importance for modern telemetry systems. Why was DQM introduced? Whenever any flight test range did telemetry link performance testing, teams would determine performance based on bit error rates. To do that, the range would send a known pattern, detect it, compare it to what it should have been, log errored bits, and then determine the rate at which the errored bits were occurring, BER. This is great for link testing, but how would a range know how well a link is performing at any given time when Project X is flying in a test range? Typically, test articles transmit the same telemetry signal on two different polarizations. A pre-detection diversity combiner combines the two analog signals into an improved lower error rate data stream. Independent demodulators and bit sinks then process the resulting three streams, the two transmitted signals, and one combined signal resulting in digital clock and data streams provided for downstream processing. For telemetry links being received at one ground station, this analog diversity combiner method was great. But to combine the same transmitted telemetry stream across multiple ground stations, a method of assessing and communicating link quality was needed that didn't rely on analog diversity combiners. Over time, ranges and the industry developed methods for determining how well the receiver, more accurately the demodulator, thought the link was performing without knowing the actual transmitted bits or having access to the pre-D analog signals. A format for conveying this information was standardized as a data quality metric, or DQM. Today, most receivers assess link quality, assign a DQM value, and convey that via a framed format called data quality encapsulation, or DQE packet. Centralized equipment can now use the DQM value to determine the best source dynamically across multiple ground stations. Let's talk about the standardization of data quality measurement. As previously mentioned, before DQM, there was no consistent way to measure and report the quality of telemetry data across different systems and platforms. The introduction of DQM standardized this process, allowing for a uniform assessment and comparison of data quality. Real-time error probability assessment. DQM provides a real-time measurement of the probability of error for a group of bits. This is critical for systems that rely on high data integrity, as it allows for immediate identification and correction of data issues, ensuring reliable data transmission. Improved telemetry receiver functionality. With DQM, telemetry receivers can generate a serial data stream that includes a standardized measurement of the real-time probability of error. This functionality is essential for optimizing the performance of telemetry data processing equipment, such as best source selectors, which require accurate data quality metrics to function effectively. Why is DQM important for modern telemetry systems? Deployment of multiple receiving sites is typically why DQM is very important for modern telemetry systems. Modern telemetry systems often deploy multiple receiving sites to support flight tests. The visibility of the test article is limited by the altitude of the flight or mission. Multiple antennas ensure coverage of a wider area, enhancing data reception quality and reliability. Multiple antennas for different look angles. Multiple antennas provide different look angles, preventing issues such as masking and onboard radiation nulls, which can occur depending on the test article's maneuver. This setup ensures consistent data reception from various look angles. Best source selection for real-time data. The primary role of BSS is to ensure that the program staff in the telemetry room receive the best possible telemetry data in a real-time scenario. Data quality metric plays a crucial role in this process, providing accurate real-time data quality metrics that inform the selection of the best data source. In summary, DQM was implemented to standardize data quality measurement, provide real-time error probability assessment, enhance telemetry receiver functionality, and improve overall data quality control. These capabilities are essential for the effective operation of telemetry systems, especially those involving multiple receiving sites and antennas, to ensure comprehensive data coverage and reliability. Let's go to the next. What is DQM? Defined in IRIG 106 Appendix 2G, DQM is a standard measurement used to assess the quality of received telemetry data. It is determined in the telemetry receiver's demodulator and involves calculating the real-time probability of error for a group of bits. This metric is crucial for ensuring the accuracy and reliability of telemetry data transmissions across different systems and platforms. DQM is not alone. There's also DQE. In addition to DQM, the IRIG 106 standard includes DQE, Data Quality Encapsulation. While DQM provides a metric for data quality, DQE defines the transport of this metric along with the associated telemetry data. Together, DQM and DQE provide a comprehensive solution for monitoring and managing the quality of telemetry data. Get ready for a zoomed-in equation. Take a screenshot if needed. The DQM equation is next. The DQM equation. Understanding the DQM equation is crucial for ensuring accurate data quality assessments in telemetry systems. Please take a screenshot for those who really want this. The data quality metric is calculated using the likelihood ratio, LR, of the received bits. This formula involves a logarithmic transformation of the likelihood ratio of the received bits. The likelihood ratio, LR, is derived from the estimated probability ratio of the received bits, which reflects the probability of bit errors in the data stream. The likelihood ratio, LR, is a critical component in the calculation of DQM. It is calculated by comparing the probability of receiving a bit correctly versus bit error probability, or BEP, the probability of receiving it incorrectly. The resulting DQM value is mapped into a 16-bit unsigned integer between 0 to 65,535, representing different levels of data quality. A lower DQM value indicates poor data quality with a higher probability of bit errors, while a higher DQM value indicates good data with a lower probability of bit errors. In summary, the DQM equation provides a standardized and reliable metric for assessing data quality in telemetry systems. By calculating the DQM using the likelihood ratio, telemetry receivers can generate a precise measurement of data quality. Let's look how to read this data in the next. As we continue learning what is DQM, let's understand how to read it. DQM is a metric used in telemetry systems to assess the quality of received telemetry data. It is calculated at the telemetry receiver's demodulator, and the process begins with estimating the bit error probability, BEP. BEP is derived within the demodulator and is the starting metric for further calculations. From this, we derive the likelihood ratio, LR, then transform the LR logarithmically to calculate the DQM. Calculated from LR, fitting with the 16-bit unsigned integer, as mentioned previously, 0 to 65,535, this standardized measurement helps ensure consistent data quality assessments across different telemetry systems. Interestingly, the process is reversible. We can determine the likelihood ratio from the DQM and use the exponents of the likelihood ratio as a representation of the DQM. For example, if DQM equals 3, then bit error probability is 1e minus 3. If DQM is 7, then the bit error probability is 1e to the minus 7. To ensure clarity, we arbitrarily cap DQM at a maximum value of 10, signifying a perfect data quality scenario. By using DQM and DQE together, we not only have a reliable way to estimate data quality, but also a standardized method to transport these metrics with the associated telemetry data, thereby enhancing the efficiency and reliability of the telemetry data processing equipment, such as best source selectors. Let's look at how this data would look on a chart next. DQM versus bit error probability, and then a reverse chart, bit error probability versus DQM. The first graph is DQM versus bit error probability. The x-axis, you have bit error probability. The y-axis, you have data quality metric. This graph shows how the DQM varies with different values of bit error probability. It uses the logarithmic scale to display the relationship more clearly. As bit error probability decreases, indicating better quality, the DQM value increases. The second graph, reverse bit error probability versus data quality metric. The x-axis, we have data quality metric. The y-axis, we have reverse bit error rate probability. This graph demonstrates the reverse calculation, showing how bit error probability can be derived from DQM values. The relationship between the two metrics illustrates how small changes in DQM can correspond to significant changes in bit error probability. Let's look at DQE next. What is DQE? How does it relate to DQM? Data quality encapsulation is also defined in IRIG 106 Appendix 2G. It specifies how to package the data quality metric for transport. DQE standardizes the format for telemetry data and the associated DQM, ensuring that the data quality metric is encapsulated within each packet. This encapsulation is crucial for maintaining the integrity and reliability of the data during transmission. Transport to best source selectors. DQE ensures that the encapsulated data, including the DQM, can be reliably transported to systems such as best source selectors. These systems depend on accurate data quality information to select the best possible data source, ensuring optimal operation. If you look at the table below, it shows the package and the message format used by DQE to encapsulate the DQM with the telemetry data. This format ensures that the data quality metric is consistently included with each data packet, facilitating comprehensive data quality analysis during transmission. In summary, DQE plays a vital role in telemetry data transmission process by standardizing the encapsulation of the DQM, ensuring reliable data transport, and supporting systems that rely on accurate data quality metrics for optimal performance. Let's take a look at the next slide. Going very detailed into the DQE format, this DQE format is designed to encapsulate telemetry data along with its associated data quality metric, ensuring a comprehensive and standardized method of data transmission and quality assessment. The DQE packet begins, as we mentioned, with the 16-bit sync pattern represented by a hexadecimal value 0xFAC4. This sync pattern, transmitted by the most significant bit, MSB, is denoted as a binary number 1111 0101 1000 Following the sync pattern are two 8-bit reserved words. These fields are currently reserved for future use and could potentially be utilized for indicating the packet header version or tagging the source ID of the data. Next, the packet includes the 16 data quality metric, 16-bit data quality metric. This metric provides a standardized measurement of the real-time probability of error for a group of bits. Again, crucial for assessing the quality of received telemetry data. The main component of the packet is the payload data, whose length is user selectable. The payload length can range from 128 to 16,536 bits with the default value of 4,096 bits, allowing flexibility in data volume and transmission efficiency. This structure ensures that telemetry data is transmitted with a high integrity and reliability, enabling effective data quality assessment and management. Now let's figure out how we can access the data quality. How to assess data quality. Assessing data quality in telemetry systems is critical for flight test ranges. We will explore why measuring the bit error rate, BER, is often impractical, and how the bit error probability, BP, offers a more effective solution. Measured BER is not practical because it requires known data. In scenarios with low BERs, measuring BER directly becomes extremely time-consuming. This process involves analyzing a large volume of data to detect a sufficient number of errors, which requires knowledge of the data being sent. This is possible only when testing a link, since actual mission data is not only unknown, but it's often encrypted. We have a solution. Bit error probability does not require known data. An unbiased quality metric. So let's talk about it. Bit error probability provides an unbiased quality metric regardless of the specific channel degradation. It reflects the probability of bit errors in the received data, offering a reliable measure of quality data. Easily determined from demodulator statistics. Bit error probability can be determined using statistics from a telemetry receiver's demodulator. This method leverages existing data processing capabilities to provide real-time quality assessment without additional complexity. DQM is calculated directly from the bit error probability. As previously mentioned in the equation discussion, DQM is calculated directly from the bit error probability. This direct relationship ensures that DQM provides an accurate and standardized measurement of data quality, enabling effective monitoring and management of the telemetry data streams. In summary, while measuring BER has limitations due to the need to know of the data, the use of bit error probability offers a practical and efficient alternative. By estimating bit error probability from the demodulator statistics and using it to calculate DQM, we can achieve accurate and real-time data quality assessments. Let's see what's next. Benefits to integrating DQM. Real-time quality monitoring. Integrating DQM allows system operators to monitor the quality of data in real time. This real-time monitoring capability can help the quick identification and rectification of issues that may affect the accuracy or reliability of the telemetry data. By addressing problems promptly, we can maintain high data integrity and ensure reliable data transmission. Enhance system reliability. DQM enhances system reliability by enabling operators and systems to dynamically adjust to varying conditions. For instance, if data quality degrades due to noise or interference, the system can employ error correction techniques or adaptive modulation to maintain data integrity. This adaptability is essential for improving operational efficiency and mission readiness, as it ensures the telemetry system can perform reliable under different conditions. Improve decision making. The availability of real-time data quality information significantly improves decision-making processes. Operators can prioritize data streams based on quality, ensuring that critical decisions are made using the most reliable data available. Additionally, the use of spatial diversity, where multiple data streams are received from different angles or locations, further enhances the data integrity and reliability. In summary, the integration of DQM provides several key benefits, including real-time quality monitoring, enhanced system reliability, and improved decision-making. These benefits are crucial for ensuring the accuracy and reliability of telemetry data, which are extremely essential for successful missions. Practical uses of the data quality metric and the data quality encapsulation in telemetry systems. Best source selection metric. DQM and DQE are critical components in the best source selection system. BSS systems are designed to choose the best possible telemetry data stream for multiple sources in real time. By utilizing DQM, best source selection can objectively assess the quality of each stream, ensuring that the highest quality data is used for analysis and decision making. Real-time telemetry link quality logging external to a telemetry receiver. The use of DQM and DQE allows for real-time logging of telemetry link quality external to the telemetry receiver. This capability is particularly useful for monitoring and assessing the performance of telemetry systems during live operations, ensuring that any issues are detected and addressed promptly. Lab and operational testing tool. In both laboratory and operational environments, DQM and DQE serve as valuable tools for testing and validating telemetry systems. By providing a standardized metric for data quality, they help engineers and technicians identify and resolve potential issues, ensuring that the systems perform reliable under various conditions. Best source selection, troubleshooting, and performance assessments. DQM and DQE are instrumental in troubleshooting and performing performance assessments of the best source selectors. By analyzing the data quality metrics, technicians can identify sources of errors and inefficiencies, leading to an improved system performance and reliability. Telemetry acquisition chain health monitoring. Continuous monitoring of the telemetry acquisition chain's health is crucial for ensuring the data integrity. DQM and DQE provide the necessary metrics to evaluate the overall health of the telemetry acquisition chain, enabling proactive maintenance and timely interventions to help prevent data loss or corruption. In summary, DQM and DQE play vital roles in enhancing the reliability and performance of telemetry systems. Their applications in best source selection, real-time logging, testing, troubleshooting, and overall health monitoring ensure that telemetry data is accurate, reliable, and ready for critical decision-making processes. Let's look at calibrating DQM next. Welcome to our discussion on calibrating the data quality metric under various channel impairments. Here, we will cover the essential types of impairments and how they impact DQM calibration. Let's start with AWGN static level. Additive white Gaussian noise is a common noise model used in telecommunications. The static level refers to a constant noise level applied to the signal, which helps in understanding the baseline performance of the telemetry system. DQGN, dynamic level step response. Dynamic quantized Gaussian noise involves changes in noise levels over time, modeled as a step responses. This helps evaluate how the system adapts to sudden changes in noise conditions. Dropouts. Dropouts refer to a brief interruption in the signal. Calibrating DQM in the presence of dropouts assessments the system's resilience to intermittent signal loss. In-band and adjacent channel interference. This involves interference from signals within the same band or from adjacent channels. Evaluating DQM under these conditions help ensure the system can effectively handle interference from other sources. Phase noise. Phase noise is a type of noise that affects the phase of the signal. It is crucial to calibrate DQM under phase noise conditions to maintain accurate signal integrity. Timing jitter. Timing jitter refers to variations in the timing of signal pulses. Calibrating DQM for timing jitter ensures the system can accurately measure data quality despite these timing fluctuations. Static multipath. Static multipath involves signal reflections that cause multiple delayed versions of the signal to arrive to the receiver. Testing DQM under these conditions helps in evaluating the system's ability to manage such reflections. It is important to calibrate your systems to ensure not only that the data quality metric under these various channel impairments will ensure telemetry systems can maintain high data quality and reliability in these diverse and challenging environments. Let's go to the next topic. Test methods for DQE and DQM. Now that we understand DQM, DQE, the calibration methods, now let's discuss the test methods. In IRIG 118.2.2, Chapter 11, defines 6 standard DQM tests. 11.1 is BER versus estimated BEP, DQM, with additive noise. This test measured the bit error rate against the estimated bit error probability under conditions of additive noise. It helps in understanding the performance of the telemetry system in noisy environments. 11.2 is estimated bit error probability, DQM, step and dwell response. This test examines how the estimated bit error probability, represented by data quality metric, responds to sudden changes, steps, and stable conditions, dwell. It is crucial for assessing the system's ability to adapt to varying signal conditions. 11.3 is BER versus estimated bit error probability, DQM, with adjacent channel interference. This method tests the impact of interference from adjacent channels on the BER versus estimated bit error probability. It is essential for evaluating systems' robustness in environments with multiple competing signals. 11.4 and 11.5 test methods are similar in a way. They are both bit error BER versus bit error probability for static 2-ray multipath channel conditions, and then 11.5 is for static 3-ray multipath channel conditions. These tests investigate the BER against the bit error probability in static multipath conditions, where signals may reflect off surfaces, causing multiple rival paths. The 2-ray and 3-ray models are commonly used to simulate such conditions. The last test method is 11.6, DQM, bit error probability, resynchronization response. This test assesses the DQM's ability to resynchronize and accurately estimate bit error probability after a loss in synchronization. It is vital for ensuring the system can quickly recover and maintain data quality after disruptions. These test methods are designed to comprehensively evaluate the performance and reliability of telemetry systems, ensuring that DQE and DQM metrics provide accurate and useful data quality assessments under varying conditions. Now, let's take a look at the RM6300, which is what we're going to be providing a live demonstration on with DQM. So let's talk about that next. The RM6300 Ultimate Telemetry Receiver Test Solution. RM6300's role as a third-party independent telemetry test signal simulator is agnostic to any telemetry receiver vendor and is used for receiver performance testing, with various tests referenced in the RCC Telemetry Systems RF Handbook and IRIG 118. The RM6300 excels as an independent telemetry test signal simulator. As mentioned, it's agnostic to all the telemetry receiver brands, and it's designed for stringent verification of telemetry receiver performance. It's aligned with protocols in the RCC Telemetry RS Handbook and IRIG 118, making it a universal tool for telemetry testing. It has dual RF output innovation. Equipped with two dual RF outputs, the RM6300 facilitates the generation of two separate RF signals simultaneously, covering a broad frequency spectrum from 400 MHz to 5,250 MHz. This unique feature enables simultaneous varied signal condition evaluations, essential for advanced telemetry testing scenarios. Wide frequency range for versatile testing. As mentioned, the frequency range, this ability to generate signals across that frequency range of 400 to 5,250 megahertz, the RM6300 offers unmatched testing versatiles across UHF, L, S, C bands, and we also have optional P band as well. This broad coverage ensures comprehensive testing capabilities across diverse telemetry and communication systems. Advanced modulation support. We offer several different modulation formats: BPSK, QPSK, OSQPSK, 8 PSK, 16 PSK, and there's many others. Up to 50 megabits per second, along with ARTEM range tiers 0, 1, 2, and also up to 50 megabits per second. Integrated testing suite. This is an all-in-one solution. The RM6300 combines functionalities that typically requires multiple devices, noise source, up converters, amplifiers, BERTs. Our unit streamlines all of this into one unit. You could access it from the touchscreen panel in the front or remotely access it through a web GUI with your web browser. Customizable testing environments. It boasts programmable features such as frequency sweep, decay, fade, Doppler simulation, noise generation for EBNO, and signal-to-noise ratio measurements. And automatic, we have DQE, DQM estimation versus actual BER measurement, offering precise simulation of operational conditions. And then, as mentioned, the versatile connectivity and control. We have, designed this for convenience. with the I and Q analog outputs for external vector modulation, data encoders featuring conventional encoding, and PCM conversion. Let's go ahead and dig a little bit deeper of how it looks on the back of this unit. So let's look at the back of the RM6300. We mentioned the dual RF outputs for testing, again allowing for the generation of two distinct RF signals across frequency ranging from 400 megahertz to 5,250 megahertz. Each output can be individually controlled for frequency, modulation, power level, etc. This is enabling, concurrent testing scenarios with varied signal conditions. You got N-type connectors for those dual RF outputs. The TTL data clock inputs is unmatched configuration options here. So 12 BNC female connectors for TTL data clock inputs. This is how we stand out to the competition for the capacity to accommodate a wide array of data and clock signals, enhancing the device's ability to simulate complex digital signal environments accurately. Precise encoding and modulation. These inputs are fundamental to our simulator modulation capabilities, supporting various encoding schemes and ensuring the generated RF signals closely replicate real-world or specified test data patterns. Received signals and remote control for seamless integration. So there's LO reference, input and output, an essential feature for systems requiring precise frequency accuracy. Our simulator acceptance of an external 10 megahertz reference signal ensures high precision in frequency generation and stability. Ethernet remote control, as I mentioned, we have a LAN remote control feature where you can basically connect to the unit with any web browser via TCP/IP, ensuring you're in the same network octet, and then ensuring optimal signal transfer. So we have impedance matching, emphasizing the importance of impedance matching. Our simulator is designed to ensure optimal signal transfer between the device and the connected receiver, which is pivotal for accurate and reliable testing results. Let's go ahead and look at how you connect our simulator to one of the receivers. The RM6300 external connection with the receiver. This is a typical way to connect the RM6300 to a system for BER measurements. The RM6300 RF output is connected to a receiver's RF input. The receiver's recovered clock and data outputs are connected to the simulator's clock and data inputs. For this example, the BER test is configured to use RF1 output and expect clock and data to return for analysis on channel 1I as displayed in the image here. Next, we'll go over briefly what the GUI looks like. Here is the TCP/IP web version of the graphic user interface here, the GUI. Again, if you're in the same network octet and you could ping the IP address of the RM6300, you should be able to navigate with your browser to that IP address. And it's a very intuitive interface for enhanced control. So as you know, there's a front touchscreen panel, but we're kind of discussing the web browser version. This is really for remote access. This dual access approach ensures versatile and user-friendly control, making the simulator sophisticated functionalities accessible to all user levels. So you see the start of data is on the left, and then the finish of data is on the right. So we're going over all of these components here. A snapshot of the device's current configuration and operational status is instantly available on the summary slide here. Configuration menu, that's at the top right. That's central to the GUI. The configuration menu is where users can adjust the system settings, including output configuration and network parameters. This menu is a cornerstone for tailoring the RM6300 to specific testing requirements. Then you have data source configuration. That's on your left. That allows the user to choose between internal and external data sources, as you can connect your own data source to our simulator instead of us generating within. Modulation options. Again, we mentioned the modulations options in previous slides, but this is where you would select it. Then you have your BER test modules, dedicated modules for configuring and monitoring bit error rate testing. And then we have the RF output configuration. These are the controls for adjusting the RF output setting, including frequency, power level, modulation parameters. This is the precision that all of your team members want when testing out a telemetry receiver. Your RF, your system status and control, so comprehensive information, the health, status reports, calibration data, and this again helps with the optimal parameters. This section is vital for maintaining reliability and for troubleshooting telemetry receivers. There's a quick start guide for streamlined operational use, step-by-step instructions how to use our system, and then advanced system settings. This is customization for experts, really for those deeper analyses, troubleshooting areas. The advanced setting offers sophisticated configuration options. This feature allows for fine-tuning beyond standard operational parameters, accommodating specialized testing requirements. So this is kind of the visual aid. Let's get started with the live demonstration real quick. Now we will start our live bench test example with the SRI's RM6300. Actual part number is 6322. But this is commonly used today in many Department of Defense flight test ranges and civil flight test ranges. But thank you so much. We're being joined today by Todd Gross, Summation Research's president. Thank you so much, Todd.
Well, thank you, Ashley, and thanks to all for staying with us this far. This is the setup we have for you today. On the top, we see the rear of an SRI RM6322 RF telemetry signal simulator. This is generating internally generated PRN and outputting an RF signal and an S-band link that is connected to a representative receiver. The receiver recovers the signal and outputs the clock and data, which is then connected back over to the signal simulator for analysis. What we're looking at here is the simulator's user interface as GUI in a browser. Starting at the left, we are internally generating a 2 to the 15th PRN sequence, NRZL encoded. We are modulating that with a Tier 1 SOQPSK TG modulation at a data rate of 10 megabits per second. We are then outputting that as an RF signal at 2200 megahertz at a power level of minus 78 dBm for cabling over to the receiver. The receiver recovers the clock and data and returns it to one of the BER inputs, or one of the TTL inputs, to the signal simulator. Here we see our 6 BERTs. Only one is connected, so we will declutter the screen here a bit and get back to our single BER. So as we look through the BER widgets, we can look at information here. We see in clock, we're seeing data input. The signal is synchronized. It is not inverted. We see the calculated BER in here, number of bits, number of errors, and the frequency, which is going to vary, plus or minus right around 10 megabits per second. We see from this that DQE is enabled. Let's look at one where it's not enabled. We see that it's grayed out there if it's not enabled. Since it is enabled, we now see additional information on the bit error probability for the maximum and minimum bit error probability for the sampling period of 1 second. And then we see the average BEP, average data quality metric, converted to BEP for that period. So we are seeing a BER estimate of about 6 and change, e to the minus 6, and our BEP is estimating about 1.3 e to the minus 6, more or less the same. We represent the data quality metric as a BEP, makes it easier to compare to the BER measurements. So in this case, if we say increase our signal, right now we're at 2, we're about 6 minus 6. We'll increase our signal level by 3 dB, down to minus 75. I'll reset here since we've been running for a little bit. And now we should see a better bit error rate. Fewer errors, yep, see 3 give or take, 2 or 3, e to minus 8, and the BEP is tracking that. And if we go on the other side and decrease it by 3, we're seeing conversely a drop. Let's reset it again. And we're seeing a degradation to 5e minus 4, give or take, and 1e minus 4 on the DQE estimate. So let's go back to our 78 here and reset. And now let's run a test. As Ashley went through previously, there are a number of qualification tests for determining the accuracy of the data quality metric. What we'll do today is we will look at a test, in this case, a familiar waterfall curve. We'll set up our test. In this case, we can either use the 118 test for BER versus estimated BEP with additive noise, which is 11.1, uses a system-generated noise to run the test in a very controlled manner. In this case, we're going to look at a somewhat more practical test where we're actually going to use the system noise floor to generate that BER curve, and we will vary the output power from signal power from the simulator to be able to generate those errors. So in this case, we are looking at let's see, we're outputting on RF1 into the receiver. We're inputting on channel 1 from the receiver. I have set an error threshold of, we want to see at least 500 bits in error to declare a valid point measurement. And we have a bit threshold of 120 million bits. Once we get to the very high signal levels, you want to call it off at some point. So we're calling it off at 120 million bits for that. For this test, we're starting at minus 90 dBm, a lower signal level, and we're stopping at minus 74, a higher signal level, and we're taking measurements every half dB at this point. So we'll come back to our graph and we will begin running our test. We have a bar up here indicating it's running in a test. We can also kind of get that out of the way. So now as our test is running, we're reporting, you know what, let's open this in another window. If we can open this in a larger window, this waterfall test. Here we are. So what we're seeing here is, again, we have valid clock, we have valid data, we're in sync, and it is DQE, it is encapsulated with the data quality metric. At this point, we are displaying the max of this hash back here in the back. The orange displays the maximum and minimum BEP within a given measurement period. The blue line indicates the bit error rate. So we have the following bit error rate points. The orange line indicates the average bit error probability within those. So we got to look at what the difference is between these as we go from a low signal level and a high error rate, and we start to come down to the higher signal level and the lower error rate. Because I have this set at a fairly high number of error bits and acquired bits, it may take a little bit to run this curve. So we'll let it go for a sec, and then might be speeding it up here to get towards the end. Okay, now we've finished with our test, and we see it tracks pretty closely. As we've gotten to the higher data rates, the bit error rate is the quote-unquote measured bit error rate is really just an estimate. Technically, to get a correct bit error rate, you'd have to let that test go on forever. So since we don't want to wait forever, we put some arbitrary limits on that. And as we get at the very low data rates, you start to see that the bit error rate, because we're not waiting all that long, the bit error rate measurements will go down here towards the bottom, indicating no errors within that that set of whatever I said, 12 million bits, 120 million bits, sorry. But the bit error probability, since that is estimated by the receiver based on the analog characteristics of that signal, you actually still get a valid bit error probability as you're going towards the bottom of that. So that in sort of large form is, you can see it a little better here, it makes a little more sense on a small chart. You can see the typical waterfall curve coming along here and the bit error probability as it goes next to it. Okay. A somewhat more interesting way or dynamic way to look at this in real time is that you can also look at this as a strip chart. So let's open up our strip chart here. And we are back at about 1 to the minus 8 in probability and BER. We'll probably go back to our 78. Let's go back to 78 there to get back in a range. And we're now looking at this data on a strip chart. So we're plotting like we did previously, but this is a time representation of it. You have a minimum and maximum bit error probability, you have an average bit error probability, and you have a bit error rate for the sampling period. In this case, we're showing data every 2 seconds for that. Now at this point, it's more of a static test. You can kind of see if you get this is a 20 million bit threshold. You know, up your bit threshold a little bit and play with this, you'll actually be able to see these over time converge for a good representation of this in relation to confidence intervals, which is really the mathematically proper way to look at these. I would refer you back to the white paper that SRI presented at the last ITC in 2023, for those of you listening to the recording. You can access that either on the repository site or just reach out to Ashley or SRI, and we can point you towards that paper. So now we have this as what you might call a static channel. Let's add some impairments to it. So in this case, we're starting with our 78 dBm signal, and we will introduce a fade at a depth of 6 dB at a rate of 0.2 dB per second. So we should start to see, now we'll turn that fade, we configure the fade here, we'll turn that fade on and come back to our chart here, and now we're starting to see that that fade. So likewise, you see the bit error rate in blue and the average BEP in orange, and they're starting to track. This is a 60-second strip chart width, so we'll see a few of these up and down sequences. Likewise, in the strip charts, we can turn on. In a typical case, you might see channel 1, channel 2, and a combiner. In this case, there's nothing connected to channel 2 and nothing connected to the combiner, so you'll see these red bars indicating no sync for those. But you can also set this up to see channel 1 and channel 2 fading out of phase with each other, and then the combined signal here being relatively static in those. Let's go back to one channel. And we're seeing again these two values tracking rather closely with them. This is a e to minus 4, 1 e minus 4, 1 e minus 5, so they're pretty close. You can see them up here as well. This is a bit error rate at one point of 1 e, well, it's moving now. But we see reported up here the bit error rate for that estimate for that sampling period and the bit error probability average as converted from the data quality metric up in this section here. So with that, I will hand it back to Ashley, and we'll go to a Q&A.
Thank you for taking the time out of your day and joining us in our webinar. Please feel free to follow us on LinkedIn and visit our website, summationresearch.com. Looking forward to seeing you in the next webinar.